So welcome to this session of the 2025 P4 workshop. For this session, the speaker is Amith. Amith is currently pursuing his PhD in the College of Engineering at the University of South Carolina. He has over 4 years of professional experience and has a strong background in developing scalable and user-friendly network web applications, specializing in both front-end and back-end developments. His current research interests are in the area of data plane programming with a particular focus on P4 technology. And he is going to present this paper titled Real-Time Encrypted Traffic Classification with P4 DPDK.
Yeah, so today the agenda talk is about having a background on the traditional packet processing and how DPDK came into a picture and how P4 DPDK comes into the picture, the introduction to DPDK and P4 DPDK. And then I'll be talking about the proposed system, what has been used for this project, and I'll have some evaluation metrics where I have done some testing and I'll be sharing those results. And then comes the conclusion and what are the future works which I'm going to do on this project. So that's the agenda for this session. And coming back to this standard packet processing. And as we look in this picture, the way how the packet processing happens is like you have a network interface card and you have buffers, and the buffers actually in the kernel holds on to the packets, and the NIC actually has the ring buffers which will hold the pointers to these packets, and then the NIC actually gives an interrupt to the CPU that the packets have been there, and there's a data stored, and then it is ready for processing, and that's how the processing happens. By this, we see there's a lot of overhead being created, and sometimes, and it can completely, the speeds over the current generation right now are very high, and these speeds the speed also has to be increased in the processing so as to cope up with the amount of traffic, the speed at which it is coming has to be matched with that. So keeping this in mind, that's how we came up with this. The technology came up with the kernel bypass, where you don't even use the kernel for packet processing using this DPDK, where DPDK is called as Data Plane Development Kit. So now we don't use at all the kernel, rather we use the user space. Everything happens in the user space, and where we have this DPDK PMD, which is called poll mode driver, which polls for the packets and then uses the applications or the libraries from which is developed in using the DPDK to process the packets. And this way, all the overhead, everything is being mitigated, and that's how the processing happens at a faster speed, coping up with the current traffic speeds which is coming up. And now when you see how do you program the pipeline using P4 using DPDK. So you see the traditional DPDK it's completely written in C, the applications or the libraries, everything. And it needs expertise in C and also the knowledge of the libraries in order to program how to process the packets in pure DPDK. And you see other thing is like the number of lines you write in C for the application would be humongous and high for bigger. It's for a bigger program. You need a lot number of lines of code, and also adding a new feature or modifying a large number of lines may also become more complex. And when it comes to P4 DPDK, the number of lines to write an application for a network application using P4 DPDK as well as DPDK, when you look, the P4 DPDK takes less number of lines when compared to the DPDK. And this is one of the advantage where we can come up. And when we need to add more features, it's modular and very easy to add and deploy functions in the data plane. And they can write a high number of applications. Anyone can write a good number of applications with high performance using P4 DPDK. Now, coming with the workflow, how P4 DPDK has been implemented, you see the system. You have the flowchart written over here. You basically write the program in P4, and then you send it to the P4C DPDK. It's like a P4 combined with a DPDK backend. It's a compiler. You compile the program, which gives you a specifications file, which is like in par with the DPDK software switch pipeline. And then you use the DPDK pipeline library to convert this spec file into a complete C object. And then you send it to a C compiler. It gives you a shared object file which can be deployed, and your pipeline is ready to be used. And this is a general picture of a smart NIC where you have the packets coming in over here. You see the violet box and the blue box. The packets come in. They are hashed and they are sent into multiple queues over here, which has a receiver and a transmitter, and then which is kernel bypassed, and it is sent to the user space for using it in the application. So for this project, the proposed system, here we have control plane and data plane. The control plane is completely offline. You can call it as an offline, where you train your model in offline mode using some servers and just have all your models, trainings, rule generations, everything done in the control plane. And then once those rules are generated, these are being incorporated in the data plane, where it is called as in this project it is called as like online, where you do inline rate processing of the packets with this rules which are generated from the machine learning training model. So now when you see the control plane, we have the data set over here. The data set used for here is like a publicly available encrypted traffic data set, which is available in IEEE data port. And this data set consists of messaging applications. And I'll let you know the more about this in the next upcoming slides. And the model we have used for this project is random forest. Reason we have used random forest is apart from random forest, any other models which are complex cannot be implemented in the data plane programming using P4, because P4 doesn't support all these floating point operations. And that is the reason we have chosen random forest model. And we also, you may be thinking, well, we can also use decision trees, but decision trees, when compared with random forest, while training on this data set, random forest produced a better result. And for that reason, we have used random forest over here. And then we have done model optimizations using hyperparameter tuning. And once the model was ready, we have used this rules generation. And while converting the rules from the model to the data plane, we have come up with one of the limitations stating that the DPDK, P4 DPDK doesn't support range values. And that's where we came up with range to ternary conversion mapping. And we converted all the ranges to ternary matches. And that's how we generated the rules and then incorporated it in the P4 program for an inline encryption traffic classification. And you see in the data plane, we have an encrypted traffic coming in and in the P4 code. So data plane is completely coded in P4, and here we have extraction of features. So we have done some feature engineering in order to train the random forest model, and we have used 5 features for here. We have used inter-arrival time, minimum inter-arrival time, maximum inter-arrival time, minimum differential packet length, maximum differential packet length, and the total packet length. These are the 5 features we have used in order to differentiate between the messaging applications present in the dataset. And how do we do this? When we calculate the flow ID, we use this 5 tuple where the IP address, source IP address, destination IP address, source port, destination port, and the protocol which we are using, and we hashed it. And for each flow, we calculate these features. And these features have been calculated for every flow. And every flow, we have taken at most 8 packets. So in a particular flow, we go through all the 8 packets and we calculate all these features. And then we update the flow metrics, what's shown over here. And then we send it to the random forest inference. And then these are matched with the match action tables. And based on the metrics, and we match with the rules. And once there's a match, we go and see like how many ever trees are there in the random forest. Each of the 3 produces a classification result. And we then go with a majority voting, which means like each tree, like for example, we have 3 trees here for an example, and in these 3 trees, we have 2 trees producing class 1 and last tree producing class 2. That means as far as this majority voting is considered, the number of class 1s are more than number of class 2s. So we go with class 1 prediction. And then we store the final prediction inside a register, and that's how we read those registers to find the prediction for that particular flow. And this is what the proposed system shown over here. Now, moving forward, we will go through the results, evaluations, and the dataset description. For this experiment, we have used Fabric testbed, which is known nationwide. And if you see here, we have used 3 different servers and 3 different slices. And you see 2 of them are like equipped with NVIDIA ConnectX NIC, which is 100 gig and deployed on Fabric. And you see in one, we have the background traffic generator to show that even at a line rate, we are able to classify accurately the applications. So for that, to run it in a line rate, we are generating background traffic using the DPDK package generator. And this is deployed in one of the server. In the next server, we actually have the pipelines deployed. And another one server, we have the actual encrypted traffic data set. So we have distributed the data set 75% for training, 25% for testing, and the testing data set, whatever is there, that is in this encrypted traffic dataset server, and that's how we'll be sending those packets, which you see in blue color, towards the pipeline. And also at the same time, the background traffic has been sending the packets in violet color, which is shown in the figure, at the speed of 100 gig per second. And then the pipeline classifies it, whether the packet is like which application it belongs to. That's the experiment topology used over here, and this has been completely deployed in Fabric. Now you see the dataset used over here has 6 applications such as WhatsApp, Messenger, Telegram, Teams, Discord, and Signal. And we can clearly see the number of packets or flows per application is not balanced, it's imbalanced, as most of the concentration is towards the Teams application. And in order to balance this, we have used smooth algorithm, and we have balanced the training data set in order to make sure importance is given to every application equally. The performance results of this model, we can clearly see accuracy has been shooting up to 91%, looks good, and precision is having around 91%, indicating that there are very fewer false positives in the classification. And you can see there's a strong recall here, which is showing that there's a minimal false negatives, and it is detecting for a better. And F1 confirms there's consistent performance between all the 6 classes, and macro F1 ensures there's very even the minority class predictions are good. And you can also see this confusion matrix over here, which shows number of true negatives are high, saying that which are negative, those are being predicted true, good. And even the true positives, when compared to false positive, false negatives, is very good enough. And this is to show that the performance of these classes applications along is very good. And this shows the confusion matrix and shows a balanced performance, where you can see for Discord, that is class 1, it's showing 92% accuracy, and for Signal it shows 97. So this is WhatsApp showing 97, for Signal 93%, for Telegram it's showing 87, for Messenger 87, and for Teams 91%. When deployed on a data plane, that is online versus offline results, you could see there is a slight difference in the performance, and this could be due to various reasons inside the data plane. And one could be because of the compression or the rules compression, how the rules have been actually converted, how the model has been converted into rules. And some can be because of the packet processing, and some could be some noise, because of which there's a slight difference in the accuracy. But you can see otherwise it is much better. But you can see there's a difference in the applications where Messenger and Teams are considered, there's a dip, there's a significant dip when compared to other applications, whereas other applications have slight minor differences. And when we have done the throughput test results, just to see how it is performing well, and you could see that for the packet sizes varying of 1,500 bytes, with an 8 core, it is giving up to 95, 94, 95%, gig speed. And this is how the packet processing and how the throughput is happening at various stages with variable cores and variable packet sizes. And here is a slide demo I will be showing you. And this has been running inside the fabric. And you could see there are two servers right now, which server 2 has the pipeline deployed, and server 3, where we have the encryption traffic classification data set. And background, the server 1 is having the DPDK packet gen running. And this is not shown over here, but it is assumed that it is running behind. And now we can see we are running the application on server 2, and this is how the pipeline is built, the way the pipeline is built. And you can see we are using two pipelines here. The first pipeline represents feature extraction pipeline, where that means the code is written in such a way we extract the features of the packets per flow and store them in registers. And the second pipeline is purely used for classifying the packets. So after 8 packets in a single flow, once it has been classified and once it has been extracted, the features, a single packet with all those feature values are sent to the second pipeline where the classification happens based upon the rules which are generated from the model. And that is what is being showing over here. And the first pipeline shows the feature extraction, and the second pipeline shows the classification. And you can clearly see here where the load MAT rules, that is match action rule, match action table rules. For each feature, we have a different text file which has all the rules like minimum differential packet length, max IAT, min IAT, and then the packet length total. And each of the, after these features have been extracted and sent, we have something called as each random forest. In this random forest, we have 3 different trees. Each of this tree has a code word where it has been generated while converting from the model to the match action rules, where the start node till the end node, where how the packet is being traversed, and all those code words. It's like when you take a left to the in a particular tree, it's an appended code byte 0, bit 0, and when it goes to the right, bit 1, and that's how it traverses towards all the particular depth in the nodes in a tree and gives you a final word. So it has a various combination of code words, and whenever it hits that, and we get the predicted value. And you can see there's something called as rules voting table, and each tree you have a different voting table per combinations of it. Whichever hits that particular predictor number, the class is being sent out. Oh, I'm sorry. So we are actually accessing the registers to read from the control plane to see the predictor class. And here we are replaying the encryption traffic classification PCAP file, that is for the Discord class, using TCP replay towards the, and we are pushing it towards the server 2. And in server 2, we are using telnet to access the registers to see what class it has been stored. And now, once we have replayed the packet, you can see here the pipeline is having actually class 1, that is 0. In hexadecimal, it's like 0x1, and it shows the Discord class is 1. Similarly, we have tried it for Signal, that is class 3, and Teams also, and also for the Teams. And you can see now Teams is being sent here, and you should see class 6, and it is showing class 6 over here. And now we will be seeing for the Signal, that is the class 3. It should be predicting class 3. And after sending the packet, you can see that we are indexing the flow ID to see the class number, and it shows class 3 over here. And that's how the prediction is happening, and that's how what the system is. So in conclusion, this paper presents a packet processing scheme for the end devices, and it uses high-level language P4 and obtain high performance using DPDK. And this is how we get the inference, or I mean, like classifying the encryption traffic at 100 gig per second speed. And future work, we right now deployed the pipelines in the CPU cores of the host. Now we would be doing that in the ARM cores of the NIC, where we are having an idea where having the first pipeline implement in the ARM cores of the NIC, and the second pipeline classification to be offloaded, hardware offload to the NIC. So that is one. We want to add more applications, and this has some limitations using P4 DPDK, whereas the bit width cannot be more than 64. The accuracy is like it could be increased even further, but because of the limitation of the bit width of 64, we are not able to accommodate more number of leaf nodes. For example, I'm saying when a code word being generated from the start node till the end node, the maximum it can go, the total bit width of the code word is only 64. That's the limitation provided by the P4 DPDK language. And that's why we were not able to go even more further. And yeah, I mean, acknowledging the Fabric and the NSF grant, which we have been working on. And for the testbed, the Fabric provided us for testing the application. And for more information, you can reach out to us in this link, and I have my email IDs here. And if you have any other questions, you can post your questions in this email. Thank you.
Thanks, Amith. This is a really interesting talk, and thank you for submitting this paper. I have a couple of follow-up questions. So your focus is mainly on encrypted traffic. So how do you separate encrypted from non-encrypted traffic?
One way is to look into the port numbers of the PCAP files and see whether it is encrypted or not. And encrypted traffic is actually like not looking into the payloads. And by the way, the features which has been used for this training the model is like we have used only the headers. We are looking only into the headers. We are not looking into the payload at all. And we can do that way. And also there will be like similar packet sizes when it is encrypted, and there could be some spikes, consistent spikes when it is a non-encrypted traffic. So we can implement more features by looking into the flags of the packets to see whether it is actually encrypted or not encrypted, and also look into the port numbers.
Got it, thanks. And the other thing you mentioned in the future work, you will look into how to offload these to P4 programmable NICs. Is that something you have given some thoughts, and would that require changes in the architecture? Like, for example, is the inference something that you can offload to, or it's still going to be software?
No, as explained, the pipelines, the two pipelines. The first pipeline is be like software where we use the P4 DPDK. When it comes to the second pipeline, there are three ways to program it using Docker. You can use the DPL programming, and you can use pure DPDK. So any of these three will be used. The DPL is like the Docker programming language, which uses also P4. But the only issue with that is they don't have stateful registers. It's not, they don't support registers. So maybe we will be using DPDK and the classification. By the way, the second pipeline doesn't need a register. The registers, everything is like on the first pipeline to extract those features and store for a particular number of packets per flow. So when it comes to classification of the pipeline, that is the second pipeline, we can implement it in direct DPL or use the Docker pipeline or use the DPDK, pure DPDK to do it. So any of these three we can do where communication happens between the ARM cores and the NIC. It will be hybrid. It's not complete software, not complete hardware. So yeah, that's how I'm like, it's not pure software nor pure hardware. It will be like a hybrid. So or we would even look into maybe use the IPUs, Intel IPUs, where they support TCAMs, and they also have range support, and they do, and that way we can offload completely to the hardware and try to see that. But when for this we were using the Bluefield 3, Bluefield 2, and we are trying to see if we can somehow come up with the hybrid architecture, use the first pipeline for software and second one to the hardware, offloading only the classification on the hardware.
Got it. Yeah, that makes sense. Thanks. And
yeah, there are
actually,
issues. There are some.
Yes.
Actually implemented. And also the one which I told you, like the bit with the 64, we are trying to come up with a different way where we can use compression technique, or a different way how to use the random forest model conversion towards the roots. We are trying to optimize that way where we can accommodate more number of leaf nodes, which would increase the accuracy too. So that is another way of looking into the extension work. So this is what we were having in my mind right now.
Good. Thanks.
Yeah.
I think this concludes our session. Thanks again for the talk and for the paper, and I'll
Thank you.
be happy to hear more if you have future work
Yes.
and new publications.
Definitely, that's what I'm working on. I don't have exact results for now. I just started working on the extension paper, but yeah, once that comes, definitely I'll be sharing it.
Thank you very much.